Okay, rolling right along, we're going to be looking at chemical equations and reactions. So far, we have learned how to name type 1, type 2, type 3, and type 4 compounds, and as well, we've also learned how to name some acids. So since we've learned all those naming conventions, we're now going to apply them into chemical equations and reactions. So after this unit, I hope that you will be able to classify reactions by type, also write a balanced molecular equation, complete an ionic equation and a net ionic equation, and predict the products of reactions given the chemical names of each reactant. Okay, to do that, let's start off with a little bit of an organizational chart here. So to help organize your thoughts, you're going to start here. We have chemical reactions, and we have two different things that we're going to be looking at here. Video one, I'm going to be talking about balancing equations, and then in the second video, I'm going to be talking about these different types of chemical equations. So today, we're just going to be looking at how to balance equations and predict some products from reactants. Okay, so we're just over here on this section today. Alrighty, hopefully you remember from the beginning of the school year, we talked a little bit about this, just some ways that we can tell if a chemical reaction happened. If we see some heat or light or some sort of sound was produced, that's definitely an indication of a chemical reaction going on. If you see some little bubbles, that's an indicator that you have produced a gas. If you remember the word precipitate, that's some sort of solid that is forming as a result of your two chemicals coming together. And of course, some color changes that occur are also an indicator that you have a chemical reaction. So here's a couple signs: change in color, change in odor, the production of a new gas or vapor, if you are releasing any type of heat, or if it's difficult to reverse. Okay. So I think we've gone over these at the beginning of the year, but it doesn't hurt us to review this. If we want to look at this overall chemical reaction that's going on here, first we have to distinguish between the reactants and the products. Over here on the left-hand side, we have the reactants. Those are the two different chemicals that are going to come together to react, and then we're going to produce some sort of substance over here. Okay, so looking at this one, let me just get a pen going here. If we were to take aluminum, notice how I have a solid right here. Okay, that's solid. That S in little parentheses indicates that it's a solid at room temperature. Okay, and then we have oxygen. And oxygen at room temperature, as you know, is in a gaseous form, so you would put the G in parentheses. And as they come together to react, they will produce aluminum oxide. Hopefully now you remember how to name this. This is why we did all of this. Okay, which is a solid. So as a wrap up, the letters S, G, and L are the physical states of compounds: solid, gas, and liquid. We're going to also talk about an aqueous solution a little bit later. That means that we have dissolved something into water. Okay. If you look at these numbers here, we're going to go over this a little bit later. These are what we call coefficients. We need these coefficients to help balance out the equation. That means how many molecules are being produced at the end, okay? So this is just, one individual mole of the reactant, and then later on we need to find out how many moles of aluminum need to react and how many moles of oxygen need to react to produce this amount of molecules over here of the aluminum oxide. So sometimes students get confused. They might think, well, if I have 4 grams and put a G here, plus 3 grams of oxygen, then it's going to yield 2 grams of aluminum oxide. Well, that's not true. What we mean by this is 4 aluminum atoms plus 3 oxygen molecules yield, this symbol right here means it yields, okay, you're going to use an arrow, means it yields 2 molecules of aluminum oxide, okay. So later on when we do stoichiometry, this actually becomes very helpful because we could do a lot of different stoichiometric calculations where we do the train tracks, or we can just simply look at the equation. If I have 4 moles, okay, of aluminum reacting, Well, if we did the molar mass, which we did a little bit at the beginning of the year, hopefully you recall that aluminum is 27 grams per mole. Well, we can just simply multiply 4 times 27 to get 108 grams of, that's how much we would need here of the aluminum for this reaction to occur. And then we would take 3 times 32 grams per mole. If you remember oxygen, we have to double that because O2 only exists like this. And that would be 32 grams per mole, and we can multiply as 2. 3 times the 32 to get 96. So this is going to be very easy for us later on whenever we look at these mole to mole ratios. Okay, this is 4 moles of aluminum, 3 moles yields 2 moles. Okay, so these are called molar ratios. Okay. Let's see. Yeah. If we look here, hopefully you remember this, the law of conservation of matter. We need to make sure that the reactants at the beginning equal the products at the end. The amount of matter in a system does not change, okay? So if we input 100%, somehow we also have to output. This is the reason why we are balancing these equations and why it'll make sense hopefully here in a few minutes. So because of the principle of the conservation of matter, the equation must be balanced. Okay, and here's just a nice picture of Lavoisier, who was considered the father of chemistry, who kind of came up with this idea a long time ago, and we're using it still today. So as a review of some of the vocabulary that you're looking over so far, the reactants are the substances that exist before a chemical change, and the products are the new substances that have formed as a result. Okay, the chemical equation indicates the reactants and the products of a reaction. Sometimes we're going to see these in the form of a word equation. Don't get, confused or stumped up by these. They're not that hard. Hopefully now you remember that methane is CH4. So if you see methane, you're going to be writing these out, CH4. When you see oxygen, it's always going to be O2. Okay, never just put O. It won't make any sense. We know that this is a diatomic molecule and that these gases only exist in nature as O2. Okay, so don't forget that. And then, of course, it's going to come together to make carbon dioxide. So you would have to write down CO2 and water, okay? So we'll talk about combustion reactions a little bit later, but this is what we're dealing with. Whenever you get a combustion reaction, you always have the products of carbon dioxide and water, okay? That's something that's always a given whenever you're dealing with these hydrocarbons. Remember hydrocarbons? So if you do that and it combusts in oxygen, as you see right here, then you're always going to get, at least you can always write these down, carbon dioxide and water. Okay, so it's just a given there. Alrighty, so we're trying to balance these equations. And they're a little puzzle, and I would get a really good pencil and a nice eraser for these because you're going to be doing a lot of erasing or scooching around on your iPad and erasing these. Do not get frustrated. Eventually you will get them and they become a lot of fun. But at first, yeah, you're kind of thinking hard and you're trying to figure this out, but it does become easier with time. Okay, so just give yourself that allowance. So if I'm sitting here with 2 hydrogens, remember diatomic elements, I have to put this as H2. It only exists like this. And chlorine is another diatomic element. We put these 2 together and we're going to get some HCl. Well, this is balanced so far. Look, I have 2 of these hydrogens because it told me. I have 2 of these chlorines and I only have 1 H and 1 Cl. So we need to think about how we can balance this out. Okay, if I have 2 chlorines right here, this subscript 2 indicates that there's 2 of these chlorines. Well, the first thing I can do is go over here and put a 2 because I know I need 2 chlorines. This coefficient means that I have 2 hydrogens now and 2 chlorines. This actually distributes. Remember distribution in your algebra class. So you have 2 H's and you have 2 Cl's, okay? So now let's go and look. Okay, well, I have my 2 Cl's. Good. But do I have 2 hydrogens? Well, yeah, 2 hydrogens. So we're balanced here, okay? So we can leave these ones alone because we already have one of these. You don't have to put a 1 out here. Those are just understood, okay? But we do have 2 of these HCl's, and this should help to balance things out. As you're seeing over here, It's now a balanced equation by putting a 2 in front of here. Okay, hopefully that makes sense. You can visualize these two, and we will be doing a little lab later on, but instead of having atoms, we're going to be dealing with bingo chips and some paper clips and snowman challenges. We have a few things going on to help really solidify this content for you. So if we were to just kind of visualize, we have some just random little moles of sodium running around and chlorine. I want to just pick 2 of them, okay? And that's after I balance it, of course. Let's just say I was going to do Na plus Cl2. Cl2 has to be Cl2 because remember it's a diatomic molecule, and it comes together to make some NaCl. Well, we need to balance this. If we have 2 chlorines, I can automatically come over here and put a 2 here. I know I need 2 here, so now I have 2 chlorines. But what did it do? It also gave us 2 sodiums. Okay, no problem. I'm going to come over here and put 2 sodiums. So now we can kind of visualize this. We have 2 sodium atoms. We have this 1 chlorine molecule. Remember, Cl2 comes together and makes a little molecule here. Okay, and when we put them both together, they separate the chlorines, okay, and instead they get a little sodium attached. And notice how there are 2 molecules of this now. Okay, so that's what we're visualizing here as we look at these types of problems. So when we're balancing chemical equations, we want to definitely make sure that the law of conservation of mass is going to happen, and that we want to make sure these reactants equal the products. Okay, so like I said, make yourself a chart, do whatever it is that helps you along when you're doing these. Sometimes you can just kind of keep track of them in your head, whatever helps. Okay, so let's look here. I'd like you to determine which one of these do you think is balanced. If you'd like to, you can pause for a minute and try to figure it out. I'm not going to wait that long. You can pause here if you'd like, but so let's figure this out. Well, this one has 2 hydrogens, okay, and if I put a 2 here, that would give me 4 hydrogens, but I only have 2 hydrogens over here, so I can already tell that this one's not balanced. Now, originally, before these coefficients came in, let's just pretend like these coefficients are not here yet, okay, just get rid of those. We're going to look. This was my original equation, just Na, some water, have some sodium hydroxide, and some hydrogen gas as a result. So I have 3 hydrogens all together here on the product side. Okay, I only have 2 over here. So what I can do is come over here, and I'm going to now erase all of these and put my coefficient in. Okay, so if I do that, I have a 2 that I'm going to put here. Now remember, this 2 distributes not only to this, but also to this. So I have 2, and now I have to multiply the subscript times the coefficient. So I have 4 hydrogens here, okay? And then I have 3 over here. Well, if I put a 2 out in front here, now I have 2 hydrogens plus 2 hydrogens. I have 4 hydrogens on each side, so we're good so far. Okay, so as I said, you can make yourself a little chart. Sometimes this helps whenever you're balancing these for the first time. So hydrogens now have 4 on each side. Okay, good. So now let's go and look at our sodium. On the left side, originally it had 1, but I went and put this coefficient out here in the front. So now I have 2. So I'm going to go and put a 2 here, and now I have 2 sodiums and 2 sodiums. So that looks good. Okay, now for the last one, go look at the oxygen. We have 2 oxygens plus 2 oxygens over here, so those look good. That's really all there is to these. Okay, 2 oxygen, not 20. Okay, so when you're balancing chemical equations, you want to write a word equation for the reaction, write the correct formulas for all reactants and products, and determine the coefficients that make the equation balance. Here's another example. Is this one balanced? If you want to, you can pause and take a look at it. I'm just going to move on. Is this one balanced? Okay, well, on this side I have 2 oxygens. On this side I have 3 oxygens. No, that's not balanced, right? So we can already say no to this one. What about this one? Is this balanced, or is it okay? Okay, well, we have 2 here. We do have 2 here, And we have one nitrogen here, but hopefully you could tell me if something's wrong with this picture. Does this exist? No. Remember, those diatomic molecules can only exist like this. Okay, so we can't have this. That's not right. Okay, so let's look at this one. This looks kind of funny, and oxygen can do this. Sometimes you have to take half of it. Okay, so we have 2 oxygens over here. Well, if I take half of this, half times 2 is 1, right? So we have 1 oxygen entity here, plus this 1 here. That gives us the 2 oxygens that we're looking for. So, to review, sometimes you will have oxygen in half. Now that might look sloppy and you may not like that. So what you could do later on is go back and multiply the entire equation by 2 to get rid of that, and it'll look much prettier. Okay, so you could have 2 of these, and then this looks bad. 1 oxygen yields 2 NO2. And don't forget to put those state symbols. Okay, I'm not going to put them today, but make sure you put the gas. Well, I'll just do it because that's the correct thing to do. Even though, there we go. Okay. So an important thing to remember, the 2 to the left of the NO refers to the number of molecules present now. So we have 2 whole molecules. Okay. It's a multiplier for every atom in that molecule. On the other hand, the subscripts of 2 here and a 2 here refers to the number of atoms of that particular type. So there are 2 atoms of oxygen, okay? If I were to put a 2 here in front, hopefully you realize that there are now 2 molecules of oxygen gas, okay? So that is the difference between those. So just a couple guidelines that you can look at when you're dealing with these. Always go and deal with your polyatomic ions first because they can be, kind of cumbersome. So make sure that those are net overall to 0 like we were doing in class, and then just balance from there. Even and odd, make everything even if possible. Do the single elements last, like oxygen. If oxygen's by itself, do it last because, like I said, they can be kind of tricky. So for this example, here's that 13 halves again that we were talking about with oxygen. But if you take the entire thing by 2, it looks a lot nicer in the end. Okay, so again, oxygen can be the tricky guy. This is what I mean by dealing with these polyatomic ions first. And this is where students can get a little bit confused. Now, we did this, and this was all fine. Okay, we had to do the crisscross method, and we realized that there were 2 phosphates and 3 magnesiums as a result. When you're dealing with polyatomic ions, make sure that that subscript deals with that entire polyatomic ion. Okay, so there are 2 of these PO4s. So that's a good starting place. If I have 2 of these PO4s, I can automatically come over here and put a 2 out here in the front. So now I have 2 of these PO4s. Remember, it's not, don't get these confused. Treat that PO4 as an entire entity. Okay, so now I have 2 PO4s. I have to go and deal with 3 of these NH4s. Well, if I have 3 times 2, I have now 6 ammoniums. So let's go over here and look. We're going to have to put a 6 out here for the ammonium. Okay, the hydroxide originally had the 2 under here. And then if we put a 3 out in the front, that means that I have 6 hydroxides, which is fine because when I put that 6 out here for the ammonium, that also gave me 6 hydroxides. Remember, treat these as their own entities, okay? Let's see, what else do we need? There were 3 magnesiums here. That means we have to go and put a 3 over here. So at the end, you need to make sure that all of these balance out correctly. Make yourself a diagram or a chart or whatever this you need. Okay, you can give this one a try and see if you came up with the same type of answer. Now these are the more advanced ones, and we'll do these a little bit later on, these polyatomics, but they are coming. Okay, so just make sure that you understand how to do those and keep those as their own entities, and you should be just fine. Okay, and just to wrap this up, I think a little bit, this is getting a little bit to be a long video. More of these I could do in class with you, but sometimes you're going to see this opposite, and you're going to have the word equation for the reaction, and you're going to have to put the correct formulas in. So if you have chlorine plus sodium bromide, that will yield bromine and sodium chloride. You're just expected to actually make these out and put the state symbols, if you know them, along the way. State symbols meaning solid, gas, and liquid. Okay, so we know that chlorine only is a diatomic element, can only exist as Cl2, and that is also Br2. So this will help you right away whenever you're going to balance these out a little bit. And then we know what sodium bromide is because we've been writing all these equations out the past couple weeks. So NaBr and then NaCl. So once you're finished with this, like I said, these will give you nice starting places to start balancing. So we know that we already have 2 atoms of chlorine, so I can automatically go over here and put 2 of these. That also gave me 2 sodiums, so I'm going to go over here and put 2 sodiums. It gave me 2 bromines, which is fine because I have 2 bromines. Okay, so let's go and check and see if our answer matches this down here, and indeed it does. And as you get to know these more and more, you'll start to understand these different state symbols, which we'll talk about a little bit later. So don't worry too much about those right now. You can give a few of these a try if you would like, but we're going to be definitely practicing many of these in the classroom. But here we have the SO4. It was taken 3 times. This gives us a good starting place to put a 3 here, so we have those 3 SO4s, but also gave us 3 calciums, so I'm going to go over here and do 3 calciums, but that gave me 6 chlorines. I have 3 here, so if I put a 2 in front, that'll give me 6 chlorines. And then I have 2 aluminums, and this is already 2 aluminum, so this looks good. Let's check ourselves down here with the correct answer. Yeah, we're good to go. And this is just to help you visualize a little bit. Again, we're going to do a lab with this, but you know, we built a lot of these little molecules. Now you understand why we did these for this reason. Okay, so just you can give that a look if you'd like. Just another look at these and how they come together to visualize this a bit. And this is the last slide for today. Sorry, this is so long. But as a review and wrap up, if you see an arrow, it means yields. It's the result of a reaction. Eventually, whenever you talk about equilibrium and reversible reactions, you're going to use one to the right, one to the left. That's more an AP, so don't worry too much about that right now. Solid means it's in a solid state or a precipitate occurred, okay? You don't even worry about this one right now because it's not at our level. Liquid is a reactant or product in the liquid state. In an aqueous solution, you'll also hear this as aqueous and aqueous. So many different ways you'll hear this word. That just means that some sort of reactant or product was dissolved in some of the water. Okay, so sometimes if I just put NaCl, like salt, and put in water, I have just not made an aqueous solution. And then gaseous would be the result in the gaseous state. Okay, so hopefully this helps to get these started. We're going to start by first doing a PhET simulation online with our MacBook Airs, and then after that I have a worksheet to get these started, and that will set the stage for the next time that we do these, which will be a hands-on lab followed by what the reaction types are. Okay, so stay tuned and make sure you're watching this video and coming prepared for class. Talk to you guys soon.